Welcome back, student, to part 2 of solving exercises using Stokes theorem. Before we start solving this exercise, I would encourage you to pause this video and try to solve the exercise by yourself, and then play the video and compare your answer with the answer in this video so that you can get the benefit of solving the question and checking your answer. So in this example, we need to find the line integral FDR using Stokes theorem. So we have to invoke Stokes theorem. We shouldn't solve this one directly. Of course, sometimes we can solve this one directly, but in this exercise, we need to use the Stokes theorem. I have the vector field F, and I have the boundary curve, which is C, or the curve that is circle in the xy plane of radius 2, centered at the origin. So let's first of all write what Stokes theorem is telling us here. Stokes theorem telling us that f dot dr, it is the same as, of course this is using Stokes theorem, this is the same as the surface integral S for the curl dot the surface that has the boundary which is exactly the same as C. So this is what we need to find here. So the best idea, first of all, let's find the curl, get rid of it, and then we come back to this integral and we try to evaluate it. So let's do the curl of f. So the curl of f will be just the gradient cross product with f, and if we do it as determinant, this is I, j, k, and here I have partial x, partial y, partial z, and in the last two row I have to write the function itself, so it will be minus yx squared, the f, as well as xy squared, and e xy. And now we just need to find this determinant. So first we cancel the row and column of I, and we do the cross product with the negative. So first we have to do the derivative of y to this function, and what we will get is this. It will be directly x e x y. Why? Because derivative of y to this function, x will go down, e will stay e, and the derivative of xy squared with respect to z is 0. Second one, if we cancel the row and the column, if we do this one, this will give me y e, and this one again will give me 0. So the second part will be y e x y. Now for the third one, if we do the derivative, this is y squared minus will be y squared plus x squared. This is the curl, we just want it, and we just keep it as is. Second is we need to find a good surface that has C as a boundary surface. So let's go here and evaluate the situation. Of course, what I have here is this is a circle of radius 2, something like this. Okay, so this is 2, this is 2. And now I need to have a surface which has the boundary as the circle. So we can think about it as hemisphere, option number 1, hemisphere. If you don't like hemisphere, maybe you can have half ellipsoid, and we did this in part 1. The question part 1 was half of ellipsoid. We can have elliptic paraboloid. It could be, for example, cone, and anything. Now, each one we have to try. Maybe some of them would be easy to evaluate the integral. Some of them would be also difficult to evaluate the integral. So what I will choose in this example, I will choose S. So let S be the plane, or let's say part of the plane in the xy inside the circle. So instead of going up and then I take the surface, I'll just take this part, which is again a surface. It's called S. The boundary of the surface is the circle. So this is something legitimate that I need and I can take. So that's S. Now you need to find parameterization for S. And for the parameterization, we need two parameters. So the parameterization will be x equal u, y equal v. And of course, because I'm in the z is equal to 0, I will just keep it as 0. Of course, we have that u square, v square will be less than or equal to 1, because I'm thinking of inside the circle. And that's the suggested parameterization. Now, in order to find the integral for this one, which is the double integral s curl f dot ds, of course here we will have to have double integral over the region of the curl of f dot ru, derivative with respect to u, of the parameter, derivative with respect to v, dA. So what we need now to do is we need to find ru, rv, we need to find the dot product, and then we will get an double integral that we can solve it separately by all the methods that we have. So let's find ru, rv, and then cross product, and then we will do the dot product with curl of f. So if I go back here, I can find ru will be, of course, r of u comma v. This one just u, v, 0. Ru will be 1, 0, 0. Rv will be 0, 1, 0. So Ru cross Rv, this will become very easy because now Ru is I. This is J. You can find the cross product between Ij and it will be just K, which is 0, 0, 1. Of course, you can do it as determinant, but that's what you should get. The next step, we need to do the dot product between 0, 0, 1 and the curl. So if we do the dot product between 0, 0, 1 and the curl, if we do the dot product, the only term that will survive is the u squared plus x squared. So here what we will get is equal double integral of y squared plus x squared dA. Of course, we have to write it down in terms of u and v. And this is just v squared, u squared dA. Now, what we get, let me just write it down here. This is double integral, usual double integral that we can find by knowing what type of region do we have. Of course, the region, we already did it here. And if I do it again, it will be just v, u, it will be just a circle. A circle. So if we have double integral over a circle or a part of a circle, the best idea was, as usual, to use the polar coordinate. And for that, r will just go from 0 to 2, because here we have the radius 2, and theta will be from 0 to 2 pi. So if we just transfer this to polar coordinate, this integral will be from 0 to 2 pi, integral from 0 to 2. Now v squared plus u squared, this will just give me r squared. So I get r squared. And then there is an r extra because I'm using the changing to the polar coordinate. So I will get this integral here of r cubed dr d theta, and the integral of r cubed just 1 over 4 r4 from 0 to 2 d theta. and this will be just integral from 0 to 2 pi. If we substitute 2, this will give me 4 d theta, so the final answer is 8 pi. Now, of course, there is one thing that we need to keep in mind is the orientation. If we assume we have a positive orientation, we keep the number as is. If the orientation is negative, then this answer has to change into negative. However, in this example, we have a positive orientation. The reason why we have positive orientation because the circle is going counterclockwise, as well as the RU or V is going upward from my region. So this is my region, and this is the normal going upward for it. And that's how we solve this question. Please, in part 3, which is the most important one, because in part 3, we'll use Stokes theorem again, but we will find this one separately, independently, and we'll find this one independently, and we will verify that the two answers is the same. So please stay tuned to part 3.